Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a continuation on rational functions, which is within a unit of polynomial and rational functions of a pre-calculus course. You should have finished my video on asymptotic behavior of rational functions, so you know what asymptotes are and how to find them. So now we're just going to dive into graphing rational functions, and all this graphing of rational functions should have been seen by you in previous courses, so I'm not really going to spend a ton of time on prerequisite theory other than to mention the following. There are a couple items here. Definition of the multiplicity of a vertical asymptote. That's going to be critically important. So if you have a rational function, r of x, and it's equal to some ratio of polynomials, a numerator of x and a denominator, which is also a function of x. And if you let that be a simplified rational function, i.e. there are no common factors between the numerator and the denominator, then if x minus c to the k is a factor of the denominator, and it is the greatest such factor involving x minus c, that is, there's no other, so let's say x minus c to the 10th is a factor of that denominator. If you can't make that x minus c to the 11th because there's not another factor of x minus c, then you've found the greatest such factor of x minus c. It's the 10th factor, 10th degree factor. Then we say x equals c is a vertical asymptote of odd multiplicity if k is odd, or even multiplicity if k is even. So again, if x minus c to the 10th was a factor of that denominator, then we'd say x equals c is a vertical asymptote of even multiplicity because that k was 10 that I just mentioned. And there's something special about the multiplicity of a vertical asymptote that allows us to easily graph a rational function, or at least easily know the behavior of a rational function about that vertical asymptote. And that's where the second piece of information down here is this theorem. If you have a vertical asymptote of odd multiplicity, then the rational function has opposite behavior on either side of that vertical asymptote as x approaches c. If it's an even multiplicity, then it has the same behavior on both sides. So let me give you an example here. So let's go ahead. I'm not going to graph a y-axis. I'll just graph the x-axis and then a vertical asymptote here. Now, if you were to have a rational function, and let's just pretend its behavior as it approaches x equals c from the left is that function goes to infinity, and from the right, let's just pretend that function goes to negative infinity, then I know just from that picture that the multiplicity of c as a vertical asymptote must be odd. That is, x minus c raised to the kth power is a factor of the denominator, and that power is odd. That's the nice thing about multiplicities of the factors of the denominator as far as vertical asymptotes go, is that you don't really care about the exact power, you care about whether or not it's odd or even. So because there's opposite behavior on either side, I know that's an odd multiplicity on that asymptote. On the other hand, if somebody gave me something like, oh, I don't know, let's draw again, another vertical asymptote. Let's say that this vertical asymptote occurs at x equals c again. But this time, let's pretend that our function looks like this. So it dives down to negative infinity as x approaches c from the left-hand side, and it dives down to negative infinity as x approaches c from the right-hand side. That I know immediately that the multiplicity of the vertical asymptote x equals c must be even. And I'll zoom in and write that down. And again, it is important to know that you have, this is assuming you have already reduced the rational function down to where there's no common factors between numerator and denominator. That is critical here. So even multiplicity implies same behavior on both sides. So falling on one side implies falling on the other. Odd multiplicity just implies opposite behavior. That really helps out when you're graphing, because then you could say something like, well, I know that it's going to infinity from the left-hand side. The multiplicity is odd, so it must be jumping down to negative at infinity on the right-hand side. That's going to be super powerful when we graph. So here is our first full example of graphing a rational function. And if you're in my class, if I ask you to graph a rational function, I implicitly mean be very careful with drawing out the graph, label all intercepts and asymptotes, state the domain, basically give me everything you possibly can about that graph. And in fact, I even really appreciate proper behavior near the zeros of the function. And I'll see if any of my examples here showcase that. The first thing you're going to do is just factor. Just go through and factor this. Now that numerator is easily factorable. Now that numerator in this case, normally we go to factor everything, but if you notice, that numerator is actually not factorable. I originally looked at this and thought it was. I thought, oh, that's gonna be a difference of cubes, but it's totally not a difference of cubes. So you're kind of stuck with the numerator as it is. However, I would like to try to factor that denominator. And that denominator does not look easily factorable. Not that I can see offhand. 4, 6, nope, that's not easily factorable. However, I will use the rational roots theorem, a prerequisite for this material anyway, to go ahead and see if I can find a root for that polynomial in the denominator so I can start factoring it using the factor theorem. So what I'll do is I'll scroll over off to the, actually I have more room over to the left, so off to the left, I'll just do my work, my scratch work over here. So that's the polynomial that's in the denominator. And I would really like to factor that. Well, the rational roots theorem tells me that I'm going to look at the factors of the constant and divide those by the factors of the leading coefficient. And again, if you've ever seen my video on the rational roots theorem, you know that I don't really care about the sign of the constant or the lead coefficient, to be very honest with you. I'm just more worried about what's the magnitude of the constant, what's the magnitude of the leading coefficient. Now the factors of both of those are going to be what's important in this case. So the factors of 28 are plus and minus 1, plus or minus 2, plus or minus 4. Let's see what else we have. Plus or minus 7, plus or minus 14, and finally plus or minus 28. Luckily, the leading coefficient is just a 1, so we don't have a lot, but I mean, there is a lot actually. When I'm looking through this, there's quite a few choices, but I'm going to start just by looking at plus or minus 1, then plus or minus 2 as the candidates for the rational zeros for this. And I should just remind you, it's really the ratios of plus or minus 1 to whatever these numbers are, but luckily those numbers are just plus or minus 1 as well. So I'm not really going to worry about labeling like plus or minus 1 divided by plus or minus 1. That's silly. So instead, I'll leave it as just plus or minus 1 and then move on to plus or minus 2. Using synthetic division, we'll try 1. We'll see if 1 is a 0 of that polynomial. If it is, remember x minus 1 must be a factor. This is how you start to factor. So there are a couple ways to check this. 1 is very fast, so if you want to do it the quick way with a 1, you can. If 1 were a 0, you could just plug it in. 1 minus 3 times 1 minus 24 times 1 minus 28. You know that's non-zero. Or, so that's me just plugging it into the polynomial. If you know it's a 0, or if it is a 0, it will turn that polynomial into 0. But we know it doesn't. That's the same thing had I just checked with synthetic division here. So synthetic division, had I tried the 1, I would have gotten, let's see, our coefficients are 1, negative 3, negative 24, and negative 28. Bring down the 1. 1 times 1 is 1, plus a negative 3 is a negative 2. 1 times negative 2 is negative 2, right? You just keep doing this And then you find out this is not 0, and so 1 is not a 0. You can see it's a little bit long-winded to do it that way. The number 1 is almost always easier just to plug into the original polynomial very quickly to see if it just turns into 0. After that, though, synthetic division is kind of the king of the course. So let's go ahead and try synthetic division with a -1 instead. So I'll erase all my work before. Remember, you bring down the 1, multiply it by a -1, it becomes a -1. Add those two together, it becomes a -4. Again, -1 times -4 is 4. Add those together, it's a -20. And this will be a +20, and that's non-zero. So, okay, -1 is not a 0 either. So you move on. Remember, this is my scratch work, so I'm just kind of going quickly with this. In fact, I can just reuse, right? I can just keep reusing that. If you have a digital whiteboard, it's super nice because you can just erase as you do this. So trying to, very quickly, oops, except you have to do math correctly here. -1, -2, -26, and that's -52. That's just not going to be 0. And so now we'll try a -2. All right, so we just arrived at our first 0, and that's all we really need is a single 0, because what you're going to have left after you factor the x minus a -2 out is a quadratic, and that's super nice. So let's go ahead and rewrite this polynomial right here. I'll use my blue ink here. That factors to x minus our 0, which is a -2. So x minus a -2, which is x plus 2. And then we're left with an x squared minus 5x minus 14. And that is beautiful because we've seen that specific quadratic several times already in this series of lecture videos. It's just I keep reusing the same example. So this factors to x plus 2, x minus 7, and an x plus 2. So that's going to be an x plus 2 squared. All right, so let's go ahead and write that down here. So I have an x plus 2 squared and an x minus 7. Sorry about that little wiggle there. That's just my pen acting up. So the very first step, again, factor your rational, the numerator and denominator of your rational function, if it's factorable. Technically speaking, x cubed minus 16 is totally factorable, but I'm not going to factor that, mainly because it's not going to help me out. Now you might wonder, like, well, how would I ever know that not factoring the numerator is going to help me out? Well, if it was an x cubed minus 8, I would totally factor that. That's an x minus 2 times x squared plus 2x plus 4. But this is not a difference of cubes, and so the factorization is going to involve radicals. And as such, I know that that's going to get kind of ugly. The only reason why I would factor the numerator is if I know a factor will cancel with a factor in the denominator. But because I know this will not factor cleanly, there's no point in me factoring it because it's not going to cleanly cancel one of those clean factors in the denominator, one of these guys right here. It's just not going to kill off either of those. Additionally, another reason why you might want to factor the numerator is when you go to find your y or your x-intercepts, I should say. When you find your x-intercepts, you'll let y equal 0, which means you're going to let your numerator equal 0. And we'll get to that in a moment, literally probably just a couple moments. But that's when factoring can be helpful, but it won't be helpful here. Okay, so back to the business at hand. Let's start again, as I've mentioned previously. I think I've mentioned it almost every video. Start with arithmetic before algebra, algebra before trig, trig before pre-cal, pre-cal before calculus. So what did you learn when it comes to graphing? What were the first concepts you learned? Likely intercepts. So let's go ahead and find the intercepts here. So I'm just gonna zoom in and I'll write Let's go for the Y-intercept first, because honestly, the Y-intercept is very fast with most functions. To find the Y-intercept, you just let the input be 0. I shouldn't have to say that, you know that. You could use either of the two iterations of this function or two versions of this function. However, it's often much easier when you're subbing in 0 to substitute 0 into the original unfactored function, because all of this other stuff will disappear when you plug zeros in and you get negative 16 over negative 28, or in other words, 16/28. I'll write that down. And of course, you are in pre-calculus, so do arithmetic, right? Divide both numerator and denominator of that by 4, and you'll get 4 over 7. So I happen to know that the Y-intercept occurs at 0, 4 over 7. The next thing I remember learning in algebra is to find the X-intercepts. And this requires just a small piece of knowledge about fractions. A fraction will only turn into 0. Oh, by the way, I should probably say that means we're going to solve 0 is equal to our function. But our function is a fraction. It's this piece right here. So remember, a fraction is only 0 when its numerator is 0. So really, you're just solving 0 is equal to the numerator. And this is another reason why factoring is kind of not that important for the numerator, because to solve that, I would add 16 and take the cube root. And we get this cube root of 16 is equal to x. Of course, you can actually do a little bit of arithmetic here. And there are actually a couple ways you could do this. You could do radical arithmetic, right? Where you say, oh, well, this is the same thing as, let's see, the cubed root of 8 times 2, because I know the cube root of 8 is 2. So you can say, oh, that's the same thing as 2 times the cubed root of 2. You could totally do that. However, if you don't want to work with radicals, which I personally don't want to work with radicals, you can work with rational exponents. So I would say, or, since we know that x is equal to the cubed root of 16, and I know that 2 to the power of, well, I know that 8 can be taken outside the cube root. I know that, so I'm going to work in the base of 2. I'm going to just say this is the cube root of 2 raised to the 4th. And using laws of exponents, I happen to know that can be written as 2 to the 4/3. To me, I just like working with rational exponents. However, your instructor would likely accept either of these. It just depends on whatever your instructor prefers. Make sure you verify with your instructor what they want. If you're a student of mine, I go for either of them. I don't really care. Just me personally, when I'm working on something, I like rational exponents. So zooming out, what else can we do? We found the X-intercepts. We found the Y-intercept. I should say X-intercept. There was only one. And the Y-intercept. Now, let's see, what else can you do? Like, if you think about how you learn mathematics, well, the next thing up was vertical asymptotes. I totally remember vertical asymptotes from Algebra 2. So let's worry about those. Vertical, whoops, except I should use not a highlighter, but a black pen. So vertical asymptotes, and I think I mentioned it in a previous video that I use VA for vertical asymptotes. And remember, right at the beginning of this video, or could have been at the end of last video, they all kind of mix into me, but you want to get your rational function in reduced form. In other words, if there is a factor that cancels with the factor in the denominator, you do that before you start this conversation. There are no common factors between numerator and denominator, so now I'll just quickly say -2 is a vertical asymptote, x equals -2, and its multiplicity is even. So I'm going to write that down. X equals -2 is a vertical asymptote, and I'll write even. I don't need to write out the word multiplicity. That just tells me when I write down the word even that it is the multiplicity. And then the other value of x that will cause division by 0 is 7. So I'll write x equals 7, and I don't know if you recall, but that power on that x minus 7 was odd. So I know that's an odd multiplicity vertical asymptote. And then finally, One last little thing that we have just been introduced to, or perhaps that you recall from your Algebra 2 course or your college algebra course, is the horizontal asymptote. And that was from the last video that we did. Remember, if the degree of the numerator matches the degree of the denominator, then the horizontal asymptote will just be the ratio of the lead coefficients. The lead coefficient in the numerator is 1. The lead coefficient in the denominator is 1. And by the way, the degree of the numerator and the degree of the denominator match. Therefore, the horizontal asymptote is going to be y equals, because it's a horizontal line, y equals 1 over 1. I'll zoom out and then zoom back in down to the horizontal asymptote here and say we have a horizontal asymptote at y equals, I'll even write 1 over 1, but that's just 1. And this is all the information technically that you need to graph your rational function. If you're lucky, you don't even have to write down any data points or plot any data points here. I'm going to draw out an axis. And notice I'm trying to demonstrate good behavior here. I label my axes, X and Y. The next thing to do is take a look at the size of things. So for example, what do I mean by size of things? Your Y-intercept here is at 0,4/7. So my scale on my Y-axis doesn't need to be from 0 to 10. It could be from 0 to 2, for example. It doesn't need to be a massive scale on the Y-axis. The X-intercept, well, that's at either 2 cubed root of 2 or 2 to the 4/3, whichever you prefer. It's some number that's slightly greater than 2, maybe like a 4 or something like that. You can grab a calculator and approximate that if you want. So I know my X values on my X-axis have to include that number. And in fact, I'll go ahead and grab a calculator right now and I'll just figure out what 2 to the 4/3 is. That's 2.5 roughly. And I'm going to write that in there just so I have that note to myself, roughly 2.5. I'm not going to write 2.5 on my graph. I just need that to help me know where that point is, where that X-intercept is. But the other things I need are the scales for where the vertical asymptotes go. Notice I have one all the way over at x equals 7, and then I have one at -2. That means that my scale on my x-axis has to at least go to 7 and likely beyond there because the graph exists to the right of x equals 7. So maybe I should have my x-axis go from -10 to +10. And finally, this guy right here, the horizontal asymptote at y equals 1. Well, we had a y value we mentioned earlier, 0,47. So we thought, okay, well, maybe a scale from 0 to 2 on the y-axis would be fine. And now we see we also need to draw the line y equals 1. So I might actually scale my y-axis to go from 0 to 4, just to give myself enough room to see if there's a graph above that height of 1, which there will be. So I'm going to pause the video and label my axes. Notice I didn't label every single point along the x-axis. I just labeled enough to kind of get things started. Now, when it comes to actually graphing, I go in the opposite direction. I graph my horizontal asymptote and then my vertical asymptote, then I plot some points. So horizontal asymptote was at y equals 1. Let me draw that in there. Notice I use a dashed line. I also use green just out of habit. One thing you should note about horizontal asymptotes, a lot of students think that a graph cannot cross a horizontal asymptote. That is not true. A graph can cross a horizontal asymptote an infinite number of times. It is totally okay. What a graph cannot touch is its vertical asymptote. That's why I draw the horizontal asymptotes in green, because it's okay to cross those, but I will always draw my vertical asymptotes in red because you cannot allow your graph to intersect a vertical asymptote. Speaking of which, let's go ahead and graph vertical asymptotes at x equals -2 and x equals +7. Notice the level of precision that I have here. I'm not really marking everything out, but I'm labeling everything. This level of precision is exactly what is expected of you as a student on a homework, a quiz, or an exam. Anything less is wrong. So you need to have at least this level of precision. All right, let's see. Let's go ahead and keep climbing up this ladder of things to do. I'm going to plot my X-Intercept. It's at roughly 2.5, 0. So I'll find that it's roughly around here. And I'll label it, but I'm not going to label it with 2.5, 0 because I don't want anybody to know that I grabbed a calculator. So instead, I'll label it as 2 to the 4/3, 0. That's what that point right there is. And finally, climbing this ladder even more, I need to plot the Y-intercept, which is at 0.4, which is a little bit above a half. So I'll just zoom in here and I'll plot that right around here. And I'll say it's 0.4/7. I'll zoom out. And believe it or not, that gives me the entire graph. Now you might say, how does that give you the entire graph? You only plotted a couple intercepts and now you have some asymptotes. How does that give you everything? Well, one thing you know about functions is that when you graph a function, it'll want to flow from left to right, or if you draw it backwards, from right to left, okay? But it will never double back upon itself because then it doesn't pass the vertical line test. So we know that it's as you start drawing from a point, let's say from this Y-intercept right here, if I start drawing to the left or to the right, it's not going to want to do this, because then it violates being a function. Another thing you should know, you only have one and only one X-intercept. I will see students often do this. Oh, I'm going to graph this. Here I go. Boom. And I want this to go down. If you do that, you're creating an X-intercept that wasn't originally there. There was no X-intercept there. You're not allowed to go down. You only had two choices when you left this Y-intercept to go to the left here, either up or down. One of those is totally incorrect because you'd be creating something that is not there. And that would be the down. So you know that this graph must just rise forever here. All right. So that's one thing. You also know, and I should have labeled this on here, not that my instructor wants, maybe my instructor does want me to label this, but they didn't tell me to. But one thing I do know is that vertical asymptote at x equals -2, that's an even multiplicity. So if it's rising on one side, it must be rising on the other side. It has the same behavior, mirrored behavior, because it's an even multiplicity asymptote. So that gets me over this hump, which is the vertical asymptote. Now I'm just going to continue to draw to the left here. When I do that, remember, in the long run, it's going to want to approach the horizontal asymptote. In fact, both sides of this function in the long run want to approach this horizontal asymptote. So I know it's going to fall to get to that horizontal asymptote. It's going to start falling down. Some people will say, how do you know it doesn't do this? And I would say, because then you're creating another X-intercept, which was not there. So don't do that. It just really wants to, in the long run, hug that horizontal asymptote. It might cross it, but it will always, like a magnet, be drawn to it. Well, that's the drawing to the left. Let's start at the Y-intercept and draw to the right. Okay, drawing to the right, I have two choices. I could either go up or go down. If I go up, it might just do that for a brief time, but remember, there is an X-intercept right here that it'll want to be drawn back down to. So I'm not going to say that it goes up. I'm just going to say it goes down toward that X-intercept. So it goes through this Y-intercept, and it's going to be drawn to that X-intercept. And though I didn't mention it in this problem because it wasn't an issue, but that X-intercept, if I would have factored this, that multiplicity on the X-intercept is a 1. In other words, I can show the factoring real quick. Hold on. Now, I'm not asking you to factor like that, but the reality is it does factor like that, and the power on this is 1. And so if you get a 0 from this, or in other words, if your graph has an X-intercept because of that, which it does, you use its multiplicity, multiplicity 1, to tell you the behavior as it approaches x equals the third root of 16, which is 2 to the 4/3. So it's going to look like a line going through this. So I'll just have it go through like that. Once you get through there, you have a couple choices. Continue down or go back up. Well, you don't have another X-intercept, so it's not going to go back up. So therefore, it's just going to go down from there. And it's going to want to eventually start hugging that vertical asymptote. The unfortunate piece is that I didn't draw the vertical asymptote long enough, so I need to kind of extend it down a little bit. But there you go. I still need to draw to the right. This function doesn't stop existing at 7. So I have to figure out what happens on the other side of 7, and luckily, x equals 7 as a vertical asymptote is of odd multiplicity, which means it has opposite behavior on either side. So on the left-hand side, it's going down. So on the right-hand side, it must be, oops, I need a different pen color. It must be going up. Here we go. Drawing this, remember, it's going to want to eventually hug the horizontal asymptote. There we go. That is the graph of this rational function. All right, for our next example, it looks very similar to the previous example, actually, if you compare them. The only difference between them is the power on x in the numerator, this guy right here. So we don't have actually that much in the way of extra work to do. Again, the same type of statement though. You definitely want to factor numerators and denominators. Luckily, we've already done a lot of the previous work, right? We know the denominator factors to x plus 2, quantity squared to x minus 7. I'll double check that, but I'm almost certain that's true. And it is, I just checked. And then the numerator this time can be factored. That's a difference of squares. It's an x squared minus 4 times an x squared plus 4. And that can be factored even further, because an x squared minus 4 is an x minus 2, x plus 2. Let me kind of move that over a little bit. And then we have the x squared plus 4 in the end. So far, so good. Again, when you're going to graph a rational function, you really want to start with the lowest level of your math courses and work your way up. So I always start with a Y-intercept because that just means let x equal 0. So I'm going to go ahead and write that in here. Stick with keeping this in view. So the Y-intercept here, if you let x equal 0, you'll see it's a negative 16 over 28, which again, just simplifies down to 4/7. So that's the same. The X-intercepts, those occur when your numerator is 0. And our numerator is 0 now at 2 and at negative 2, or is it? If you take a look at this, remember when you dive into this stuff, you want to make sure you simplify this as much as possible. So notice a factor of x plus 2 will cancel with a factor of x plus 2 in the denominator. And so really, we should have further simplified this to x minus 2 times x squared plus 4 all over, again, x plus 2 times x minus 7. It doesn't actually change anything about the y-intercept, for example, because that'd be a negative 8 over, what is it, negative 14, and that would reduce down to, again, 4/7. So that doesn't change. But the x-intercepts, that's kind of critical. We can see here that we have an x-intercept at 2. So I'll just say 2, 0. And actually, I'm going to make a little note now. I'm going to say that the multiplicity of that is 1. That'll be helpful. In other words, the power on the x minus 2 is a power of 1. Also, something to note. If you set that factor equal to 0, it will not give you a real number solution. That is, there's no real numbered 0 associated with x squared plus 4. And when you graph on a Cartesian coordinate system, you're only worried about real numbers. So do not worry about the x squared plus 4. It does not give you an x-intercept. So we have a single x-intercept, kind of like before actually, but just a cleaner one. As far as the asymptotes go, remember, the vertical asymptotes you can find, the vertical asymptotes you can find once you've simplified your rational function. Notice here, the powers are both odd on these vertical asymptotes. So I have as far as vertical asymptotes go, x equals -2 and x equals +7. So vertical asymptotes, x equals -2 and x equals +7. Both are odd multiplicities because they both have odd powers. Do not be fooled into thinking that -2 has an even multiplicity. It doesn't. It doesn't have an even multiplicity because it got canceled. That's critical. And then finally, the horizontal asymptote, if there is one. Well, if the power in the numerator matched the power in the denominator, in other words, if the degree of the numerator matched the degree of the denominator, then you would have a horizontal asymptote at the ratio of their leading coefficients. If, on the other hand, the denominator had higher degree than the numerator, well then, you'd have a horizontal asymptote at y equals 0. But in this case, because the numerator has a higher degree than the denominator, that means you're going to have an oblique asymptote, which means you need to do long division. So I zoom out slightly, and I'm going to go ahead and keep that HA on there, but I'm going to cross it out, and I'm going to go ahead and replace it with an oblique asymptote. And again, that's because the degree of the numerator is higher than the degree of the denominator. Off to the side, I still have to do long division to find out what is the quotient when I do that long division. Nobody cares about the remainder. All I care about is the quotient. So let's go ahead and do that. We have x cubed minus 3x squared minus 24x and then minus 28. And I'm dividing that into x to the fourth plus 0x cubed plus 0x squared plus 0x minus 16. Yeah. This shouldn't take too long. It does look like it at first, but it won't take too long because really all you're worried about is how many times does x cubed go into that x to the fourth? Well, x to the fourth divided by x cubed is a single lowly little x. You get to double check your work. Take that x and multiply it against every term in that polynomial, and you'll get that you have x to the fourth. Let's see, x times a negative 3x squared is a negative 3x cubed. X times a negative 24x is a negative 24x squared. And finally, x times a negative 28 is a negative 28x. Do not forget to subtract that entire statement. Let's see, the x to the fourths cancel by design. If they don't, then you did something wrong. You have 0x cubed plus 3x cubed, so 3x cubed. You have a 0x squared plus 24x squared, so plus 24x squared. And then you have a 0x plus 28x. You can bring down the negative 16, but you'll find out right now that there's no need to go any further because what you're going to do is take x cubed and see how many times it goes into 3x cubed. Well, that goes in 3 times. We totally know that. And notice, at this point, I have found the linear term and the constant term. Anything after this is just going to be a remainder. So I don't need to go actually any further. That's a little trick to doing this. So you could, if you want to, by the way, you could say, well, let me take that 3 and multiply it up against x cubed, so I get a 3x cubed, and 3 times a negative 3x squared is a negative 9x squared. You could totally do that. Right? Let me just go ahead and just do this very quickly. Negative 72x and a 3, that's 60, 84, negative 84. But when you subtract that entire statement, you'll see 3x cubes cancel. 24x squared plus 9x squared is a 33x squared. And I'll do this because the reality is x cubed will not go into that. So that is my remainder. Anyhow, my oblique asymptote is just this quotient right here. So I'll just grab that guy and put it right here. I know that the guidelines to graphing are going to be y equals x plus 3. That's the guidelines to graphing at the edges. Now we still have to pay attention to the scale on the axes. You're going to have the y's at least get to 4/7. You'll have to have the x's get to at least 2, nope, up to 7. So you could see scaling the x values maybe from -10 to 10 might be useful. Also, be very, very careful with an oblique asymptote, because it turns out that at, for example, x equals 0, you're going to graph this line. At x equals 0, you'll need the y value of 3. And at x equals 10, you'll need the y value of 13. So I'm going to scale my y-axis to go from -20 to +20, just in case, can fit everything in there. So let me maybe zoom out a little bit, and then I will pause the video and draw out my axes. All right, so we get down to this point. I haven't actually labeled the x-axis yet, but I will. I'm going to label it by 2's, just because it's a little bit cleaner. So this will be 2. There's no need for me to actually label anything else, because that tells you the scale. And I'll do the same thing for the y's. There we go. So every pip along the y-axis is a distance of 2. Every pip along the x-axis, again, is a distance of 2. And remember how I said to do this. I write things in the order that I learned them in mathematics. So Y-intercept, X-intercept, vertical asymptotes, and oblique asymptotes are the most recent. But when I start my graphing, I actually start at the bottom and climb. So I'm going to start here with y equals x plus 3, and I'm going to graph that. And I'm going to use a dashed green line for that. My intent was to use a dashed green line, but it was just too much of a pain, so I just went ahead with a solid green line. And I'll do the same thing with the vertical asymptotes, a solid red line when I get to those, which is basically right now. X equals -2 and +7. So I'll do solid red lines for those because, again, vertical asymptotes you can never actually run into. Horizontal and obliques, you totally can. Now notice the precision with which I've graphed this, right? So you have, let's see. Well, it was precise until I realized it wasn't. I just looked at that and thought, oh, wait a second. The slope of that's not right. So anyway, because of the way I've chosen my pips, this is a height of 3, and that's y equals x plus 3. And when x is a -3, it crosses the x-axis. So I had to adjust that green asymptote. But anyway, so this is pretty darn precise now. Notice even at the bottom, I state not only the equations for the vertical asymptotes, but their multiplicities. That will help out. Now, climbing this ladder even more, I'm going to plot the x-intercept and the y-intercept. So 2, 0, and let's see, what else am I going to plot? 2, 0, and 0,4. Now this is where the art form of graphing comes in. Notice I labeled the 2, 0, but I did not label the 0,4 yet. The reason why I did not label my 0,4 yet is because I need to know where my graph is going. I don't want to like run through my numbering. All right. So all that being said, I should note one last thing here. The thing I want to note is that x cannot be a -2. Well, actually, I was going to say that x cannot be a -2 because it got canceled here, but it still can't be a -2 because it's still a vertical asymptote. So ignore what I was just about to say. Anyhow, I have 2 points, and I will start with the y-intercept because that's typically where I like to start if you have one. If you don't have a y-intercept, let's say you're graphing something that doesn't have a y-intercept, it can be kind of difficult to know where to start graphing. At that point, just plug in x equals, let's say in this case, a 3 into your original function to see if it's positive or negative. That'll give you a start. Okay. But for me, the y-intercept is a beautiful place to start if you can. And I'll start graphing this blue function to the left. Now I have 2 choices, down or up. Now remember, if you go down, you're going to go through that x-axis, but I don't have an x-intercept. So it has to go up. It'll want to approach this vertical asymptote. It's much better when I was actually zoomed in because it's easier to graph. So I'll just graph it like that. And let's go ahead and see what happens if you had graphed. Well, maybe I should stick with this. So keep going to the left. It would have been rising forever. There's no need for me to continue to draw that because I'm pointing up means that it's going to rise forever. Considering the multiplicity of that vertical asymptote, it's odd, means that it has opposite behavior on this side. So it starts low. The reality is though, that I'm going to have to graph hugging that asymptote for so long, I'd rather start around here. It still says I'm going low. It's just, I don't want to have to draw a vertical, nearly vertical line all that time. Now you have choices as you graph to the left. You could do this, but if you do that, you're going to be violating two issues or committing two sins, I guess you could say. One, you're crossing an X axis without having an X-intercept. Two, you want the end behavior of your function to mimic that green line. So if you had done this, you'd have to come back down to get close to that green line, which means not only did you create one X-intercept, you're creating two. That's a no-no. So instead, as I graph to the left here, it's going to climb for a little bit, but then it'll eventually want to start hugging this oblique asymptote. I'm done graphing to the left. Now I will start at the y-axis, at the y-intercept itself, and graph to the right. Remember, the multiplicity of this intercept is 1. So it'll go through like a line. Look kind of like that. Let me zoom out. Now, I have options. It's either going up or going down. Well, if it goes up, you're going to make it cross the x-axis where you don't have an x-intercept. So obviously you're not going to go up. It's going to want to go down. You zoom out a little bit further, and there you go. Looks something like that. It's kind of a nice looking graph. Now remember, you're not done. You still have to hop onto the other side of x equals 7 there. It's an odd multiplicity vertical asymptote. Since it was going down on the left-hand side, it'll be starting high on the right-hand side. And as you graph to the right, again, you have your choice. You could say it's going to cross, but again, that's a no-no for two reasons. One, you're creating a vertical or horizontal intercept. And two, if you do that, it wants to come back up and go to hug that oblique asymptote, which means you're creating yet another X-intercept. So those are both wrong. Instead, it's going to go to the right, but eventually want to start hugging this oblique asymptote. That is the true graph of our original function. Oblique asymptote and all. Everything's beautifully graphed. That's the level of detail you should be going for. All right, this is the last actual graphing example, but I want to draw your attention to a special kind of oblique asymptotes. And this is, some instructors cover this, some don't. And I just noticed, probably all of the problems say this. They say state the domain. Yes, you should probably follow those directions. State the domains for each of these problems. I just didn't. But they're kind of obvious from here, so don't forget to state the domains like I forgot to state the domains. All right, so luckily we're just dealing with the same exact denominator that we have been dealing with this entire time. Remember, you want to factor everything first when asked to graph. So the numerator is factoring by grouping. So that's x to the fourth times x minus 2, minus 16 times x minus 2. That's super nice. The denominator is that, what was it? It was x plus 2 squared times an x minus 7. And let's see, this is going to be an x minus 2. And we factored it'll be x minus 2 times x to the fourth minus 16, but we factored that last time. It was an x minus 2 times x plus 2 times x squared, right? Yeah, plus 4. A lot of thinking on my toes there. And we have an x plus 2 quantity squared here, and an x plus 7. X minus 7, sorry. And remember, you do want to simplify this completely. So I'm going to go ahead and cancel the power of x plus 2 from numerator and denominator. And we get down to this beautiful x minus 2 quantity squared, and then an x squared plus 4. That 2 got a little messed up in translation. And this is all over x plus 2, x minus 7. Essentially, all the other stuff is very close to being the same. You look for the Y-intercept. So you let x equals 0 and get 4/7 again. You look for the X-intercepts. Remember, those occur when the numerator is 0. And so if I let the numerator be 0 here in this last one, you get that 2, 0 is an X-intercept of multiplicity 2, though. Its power is 2. Just write that in there. And then, again, x squared plus 4 does not contribute anything to the X-intercepts. And now we go for vertical asymptotes. Let me do that. Vertical asymptotes. We have -2 and 7 again. So x equals -2, multiplicity odd, and 7. Again, odd multiplicity. And finally, we go for the oblique asymptote. Again, because the numerator, the degree of the numerator, is higher than the degree of the denominator. So there has to be an oblique asymptote here. All right, oops, not in highlighter, but in black ink, oblique asymptote. Notice how quickly you can go through this. Now, in this case, the long division is going to be a little bit longer than the long division before. So let me pause this and at least get this set up. And I just realized right when I did this that that is not going to be a 4/7. If you let x equals 0 there, it'll have 32 over, wow, that's what I get for not paying attention, right? If you let x equal 0, you get 32 over a -28. Both are divisible by 4, so that'd be a negative, -8/7? So I'll write that in. That does make a significant difference. Mainly because your y-intercept is now negative. So that kind of shifts things a little bit here. But yeah, be very careful about that, just like I wasn't. Mainly because I've been lecturing for, it seems like, weeks. So what I'm going to do here is just automate the long division. You should just ask yourself how many times x cubed go into x to the 5th, and here I go. All right, so we get there, and now we're going to go ahead and ask ourselves how many times does x cubed go into x to the 4th? All right, and finally, we just ask ourselves how many times does x cubed go into 27x cubed? And it goes in 27 times, and there's really no need to go any further than that because, well, you're done, right? So if you multiply back, this is your quotient. Once you've found your quotient, there's no need to go any further, so I won't. So my oblique asymptote here is y equals x squared plus x plus 27. Now the thing about oblique asymptotes that are quadratic or higher in order like this is that you have to be very careful with your scale on your y-axis. And this is probably why a lot of people don't assign something like this. The scale is so significantly large on the y-axis that it can be a little troublesome to graph these. Think about just think about graphing that parabola, x squared plus x plus 27. Its y-intercept is way up here at 27. Like, that's significantly far up there. Moreover, it is actually not going to be dipping down that far. It kind of looks like this, to be honest with you. So it's a little bit of a pain. My scale for my y-axis has to go well beyond a height of 27. That's going to be challenging. So be just very aware that your y scale, the scale for your y-axis has to be massive, which makes this y-intercept really hard to accurately graph. So let's see how good we can do this, or how well we can do this. Now notice that I've really scaled this weirdly because of the fact that I know that most of my graph is going to sit above the x-axis. I've created a majority of this graph, or the axes, to appear above the x-axis. Let's go ahead and draw in the oblique asymptote. So that is going to be this parabola that goes through a height of 27. And by the way, you might want to just use the graphing method I've recommended in the past. So remember, I'm going to do it off to the side here. We have y is equal to x squared plus x plus 27. And actually, I may not have done it in this course because I teach so many different courses, it's hard for me to remember who I taught this to, but this is the way I graph parabolas. So what's the y-intercept of that parabola? Well, that's easy, 0, 27. Next question, when is y equal to 27 again? In other words, it's a hanging chain. That's what a parabola looks like. If it hits a height at one point, it'll be at that height again later on. So the question is, when is it that height of 27 again? Well, that's when you have this action going on. If you subtract 27 from both sides, you'll find out this parabola is at a height of 27 when the solution to this equation occurs. It's at a height of 27 at x equals 0 and at x equals a negative 1. Again, it's at a height of 27 at, so let's say this is the height of 27 here, at x equals 0 and x equals negative 1. Halfway between those two is the vertex. So let's go ahead and do this. Let's find out what is a good scale here. So how many pips do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Let me think. Let's scale these by 5s. If this is 5, which doesn't look like that. If this first pip is at a height of 5, then this is 10, this is 15, this is 20, and this will be 25, and this will be 30, and this will be 35, and this will be 40, and this will be 45. Just because I want to. And at 27, we have an X-intercept for that parabola. And let's also consider what is, I'm going to make that a little bit darker. What is the scale for our x-axis? Well, our x-axis has to contain our X-intercept, 2, 0, and the vertical asymptotes, -2 and 7. So if I scale by 2s, I think it'll be okay. Let me go ahead and just put that down here. I'll scale these by 2. So this would be 2. Whoops, wrong color. I'll scale these by 2. 2 and 4. You get the idea, right? -2 and so on and so forth. So let's see. I know that our parabola hits a height of 27, again at -1. So kind of halfway between here. And that's going to be hard for me to show. So let me see if I could do that. That's right around here. Whoops. Again, wrong color. So around here. Otherwise, it dips down a little bit. I am actually this time going to go ahead and dot this out. And then you might want to see like, okay, well, when x is equal to 2 for that parabola, what's the y value? If the x value is 2 for this parabola, you get 4 plus 2, which is 6, plus 27 is 33. So at x equals 2, we have a height of 33, roughly around maybe about here. So I'll go ahead and continue forward with this, maybe even a little bit higher. So it might have been, maybe I need to widen this out a little bit. Something like this. I'm not super duper duper concerned about how immensely accurate it is, because it is honestly an oblique. But it goes up like that, and it's symmetric, so it's going to do the same thing on the other side. I don't need to plot a point or anything. I'm just going to do this. There we go. There's our oblique. It's a guideline to graph when we need it. All right. So now what do we have? I did my oblique. That's done. I'll highlight that out. Now I'm going to graph my vertical and my vertical asymptotes. That's all I need to do. And once I've graphed this, I realize, oh man, this is a bit scary for me because I can see there's going to be a bit of a problem here. Give me a moment. So you can see what I did. I erased my my oblique asymptote because my scale is not going to work on my y-axis. It's a very unfortunate piece, but here's a good fix for it. So, and this happens with obliques quite often, in fact. So what you need to do is look at your x scale. Notice the scale along my x-axis goes 2, 4, 6, 8, 10, 12. It goes all the way out to 12, right? All the way to the right-hand side. This point down here is x equals 12. So if I need to graph this parabola going all the way to x equals 12, I want to include the y value for that parabola at 12. So if I plug 12 in, I'll get 144 plus another 12. So that's 152 or 156, sorry. Add another 27. So I want my y values to go to maybe 200. Yeah, you could see now why that was an issue. So I'm going to go ahead and rescale this. And the way that I did that is I chose a scale of 20s. Again, because I have x values along this x-axis, for example, I know my vertical asymptote here is x equals 7, the rightmost one. So if my function's going to follow the oblique asymptote beyond there, it needs to go to x equals 8, 9, 10, 11, 12, that type of thing. And so I need my parabola to still exist on this screen, if you will, when x is 12. So if you plug in 12, it's going to be less than 200, but it's still going to be scaled around the 200 level. So that's just a critical element. We know that at time 0, that's a height of 27. So I'll just park it right there. And then maybe at time, let's do time 4 here, just to get this going. And that'll be a y value of about 47. And then if you put time 10, which is again right about here, time 10, if you plug that into the parabola, you get 100, 110, 137. So somewhere around, again, time 10, somewhere around here. Okay, so those will be my guidelines to graphing this parabola. I'm not going to actually use the dashed lines. I'm just going to go ahead and just graph this parabola like this. So this is my oblique. It is a massively wide parabola at the scale, but kind of necessary for us to get a proper graph. Now I can actually finish this out. I apologize about that, but there we go. So we're done with the vertical asymptotes, the oblique asymptote. Now X-intercept is at 2, 0. I'm going to use blue ink for my function. So 2, 0 is right there. And let's see, the Y-intercept is at 0, -1 roughly. And remember this scale, oh man, that's a massive blue dot. This scale is by 20. So really it's something like this. Really close to the x-axis. All right, we're ready to graph. One thing I need to remind you of is that x equals 2 is an x-intercept of multiplicity 2. So it's going to look like a parabola locally near to that 0. All right, let's go to the left of the Y-intercept. Again, we now know I don't need to have that conversation anymore. We know it's going to go down and want to hug this vertical asymptote. I'm not going to bother drawing it too far down. I'll draw it maybe this far. Let's just say. And now what I'm going to do is it's going to go through that Y. Actually, maybe I should continue to the left. Notice that that vertical asymptote is odd multiplicity. So the behavior on the other side of that vertical asymptote will be the opposite. If it's going down on the right, it starts up on the left. Left-hand side of that vertical asymptote, that is. Now remember that green curve, the oblique asymptote, is a guideline for graphing as we zoom out. When we're zoomed in, we don't see it. But as we zoom out, our blue curve should follow that green curve. So that's a nice way to showcase. It's just going to do something like this. It's going to want to hug that green curve as time goes on. All right. So far, so good. Now I have my blue curve there. And let's see, let's go to the right of the Y-intercept. Remember the x value of 2, the x-intercept of 2 is even multiplicity 2. So it's going to bounce off that like a parabola. Won't go through it because A even multiplicity causes the curve to bounce off that. And otherwise, as you draw it to the right, it's just going to dive down because it doesn't want to create yet another X-intercept. And finally, because that vertical asymptote to the right there is odd multiplicity, since it's going down on the left-hand side, it'll start up on the right-hand side. And eventually it'll want to start hugging the parabola. The blue ink is the actual curve. Let me go ahead and just showcase this by erasing my parabola here so you can see my blue ink. So let's just get as much of this parabola out of the way as possible so you can actually see the beautiful graph that we have. There it is. Very pretty curve. However, a bit of a challenge because of scale. And that's the problem with the oblique asymptotes, is that you can get these massive scales. Just be very aware of that, and you'll be somewhat safe. As a final example, and you can see this is a very big section, just because working with rational functions ends up just being a massive topic, and there's no way to split it up easily. Other than to have a piece like I've had for graphing them and have a piece for talking about asymptotes separately. So now talking about this one, find the equation of the function graphed below. Well, they've given us almost everything we need. If you zoom in, you see that we have a vertical asymptote at x equals a -8. And if you zoom out, you'll see that's odd multiplicity, right? The behavior on either side of that vertical asymptote is opposite, so I know that's odd multiplicity. The other vertical asymptote is also odd multiplicity, and that occurs at x equals 2. Again, that's odd. The y equals 1 is the horizontal asymptote. The fact that you have a horizontal asymptote at y equals 1 means the degree of the numerator must be the same as the degree of the denominator, and the ratio of the lead coefficients must be 1. You also have an X-intercept at 4. So 4, 0 is an X-intercept. You have an X-intercept at what looks to be a -1. What else do we have? That's pretty much it. You might say, yeah, and I also have a positive Y-intercept. You do. But honestly, that's a little less important. What is most important is the stuff that I've listed out here. So let's think about what your rational function could be. R of x. Remember, your denominator is defined by your vertical asymptotes. And you have one at 2 and at -8. So x plus 8 and x minus 2 must be in your factors in your denominator. Moreover, they're both odd multiplicities, so they might both be power 1, but they might not. We're about to find out. Your X-intercepts occur at -1 and 4, so factors in your numerator have to be x plus 1 and x minus 4. So far, everything I've written down satisfies this graph. Additionally, if you think about what this polynomial would multiply out to be, you'd have a degree 2 in the numerator over a degree 2 in the denominator. So they match. So the horizontal asymptote would be a ratio of their lead coefficients, and luckily I have 1, 1, 1, 1. So the lead coefficient of the numerator would be a 1. The leading coefficient of the denominator would be a 1. So this rational function looks to be the winner. Let me just make sure that this is okay. The only other thing I would likely want to be careful about is the thing I told you is not a big deal, which is the Y-intercept. I don't need to know what the exact value is. I just need to know that it's positive. So let's go ahead and quickly check to see if our Y-intercept is going to be positive. Remember, the Y-intercept occurs when x is 0. So if you let all these x values be 0, you will get -4 on top and a negative 16 in the denominator, and that is a positive number. So we are okay. This is a decent function to represent the curve above. That's how you kind of create functions from given curves. You look at their vertical asymptotes and their multiplicities. You look at the horizontal asymptotes, and you look at the X-intercepts and their multiplicities. So in this case, the X-intercepts were pretty easy to see. They're both kind of a multiplicity of 1, but had they bounced off, then that would have been a multiplicity of 2. All right, this was a super long video, and there's just one more video in the series, which is not as long, but I think that it's worthwhile to cut this one now.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much, that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.